Alrighty, there we go. So piecewise functions have like a definition that we can write out here, and I'm gonna make it so you can do this, and I can actually write in a decent handwriting. Oop. A piecewise function is a function, so it's gonna pass our function rules. That has different equations over pieces, that would be where the piece comes from, of the domain. What it looks like is that we take a graph and we take a few graphs and cut them up into chunks. So a sketch of a piecewise function could look like a line mixed with a little horizontal segment and then maybe a swoop. That's a piecewise function. It's literally cut into pieces. Pieces of stuff. A stepwise function is a specific kind of piecewise function. So oh, that's a really ugly green. I don't like that color. That one. A stepwise function is a piecewise function made only of horizontal segments. So a stepwise function looks literally like stairs. Horizontal segments only. So a piecewise is just cut up into pieces. Stepwise is literally stairs. They can go up, they can go down, they can be all over the place. They can be crazy stairs, but they're stairs. I could stand on those and not fall over. Okay, so we are going to graph 3. So naturally, I don't know how to graph. I have them set up so that you can just like glue them in like this, and you have space to write on one side, and now you graph the right side up. Try to make it easy for you guys. You don't have to cut them out. You can if you want to. As always, it is your notebook. You do what you want. But you do not have to when you don't have functional space. Okay, piecewise functions look a little crazy when they're written out, okay? This is our first piecewise function. Isn't somebody singing along to the music in their head? If you got your music playing, be aware, they're singing along. quiet enough that I couldn't hear the music, but I could hear you humming. So what this is and what this means is it's literally, remember this guys, y equals this when x is less than or equal to 1, and y equals this if x is greater than 1. Literally, it's two different equations over different pieces of the domain. So the way we're going to go about graphing these is we're going to take each chunk and graph them individually. Y equals x minus 3 if x is less than or equal to 1. I need to make sure we stop when x is less than or equal to 1. So what I'm going to do is I'm going to take my domain restriction, which is what this column is, and I'm going to draw myself a line where x equals 1. My first equation, x minus 3, is going to be on this side. My 2x is going to be on that side. Literally building myself a wall. Fence. Do not cross the line. For this first one, we have our y-axis, so we can graph this just like normal. Y equals x minus 3. What's my y-intercept on this purple piece? -3. What is my slope? 1 over 1. Up 1, right 1. It's going to put it right on my little barrier wall here. We can also work the other direction. Down 1, left 1. Down 1, left 1. And get more pieces that way. Where did I lose you? So you can graph the whole thing and like wind up erasing part of it because this is that whole line. But I know my x have to be less than or equal to 1. So I'm going to freak my screen out. I'm going to break it off where x equals 1. And I cut my line into pieces. Yeah. Let me get rid of that. Let's walk through it again. So on the purple piece, we have to stay where my x is smaller than 1. So I'm just going to graph this line like normal. We're using our y-intercept. My y-intercept is -3. My slope of 1, up 1, over 1. And I put a dot right here. Because right here. -3. Okay. I just rewrote it down here so it didn't have the fancy f of x guy. Because that's just y in a fancy suit coat, mustache, and sunglasses. He's hiding in disguise. Trying to make himself look crazy. He's just y. And then if you don't like working backwards with the slope, you don't have to. From those 2 points, we can technically do it. Right there. My x's have to be less than 1, so this keeps going. But I can't go to the right of that purple barrier because of my rule up here, where x is, let's see, I gotta get to my pointer. X is less than -1, so I can't go to the right of this line on purple. It's like a wall. I crash into it. If I want to go where x is bigger than 1, I got to come down to this rule, which is what we're going to do next. That is not the shape I wanted. There we go.
So you put,
Yeah.
put a line on the X.
Wherever our domain restriction is, wherever this guy is,
You put a line.
put a line on that. That is a wall for you. It is a fence. It'll stop you.
And then wherever they meet, you just put a line.
It's going to be wherever these are listed. They're not always going to meet. Wherever one of these is listed, put a barrier. Wherever one of this is, where x equals 1, we have a barrier, so I don't need to draw another one. No, it's okay. We draw a fence where x equals 1, right? My x's equal 1 right here. This wall is because of this. I need a barrier on my green function, again, where x equals 1. So it's the same line. I don't have to draw it again. But now I'm going on the right side when x is bigger than 1. And you can graph this like a normal line and like erase pieces if you want to. But when I'm not by my axis, my y-axis, it gets annoying. So what I'm going to do is I'm going to make a table. And I'm going to pick x's and find their y's. And I'm going to pick x's that are greater than or equal to 1. 1. What's another x I can use? 2. 3. Yeah, it gets the point across, right? So if my x is 1, what's my y value? 2. 2 times 1 is 2. If my x is 2, what's my y value? 4. There we go. X is 3. What's my y value? 6. Plot those points. So my 2, 4, I'm going to put here. My 3, 6 goes up here. And my 2, or my 1, 2, we just got to be really, really careful because remember, this does not actually include 1. So we are going to do an open circle. We did these back in Algebra 1 when we would do like number liney stuff. If it's an equals to, it's a closed circle. If it's not equals to, it's an open circle. It's gonna look like this, and these are a little crazy. I am 100% okay with your graph looking just like this. If you wind up looking up like answers in the back of the book or online, they will look like this. They don't put the fence in like the answer keys. So this is what things like answer keys will look like. Yours can look like that. I'm 100% okay with that. If you don't like the barrier, you don't have to put the barrier. I feel like the barrier makes it easier to see. So I do not care how your picture looks. Either way is fine. I'm going to put the barrier back. Okay.
Why is the purple one not open?
The purple one is not open. Excellent question. Because this includes 1. This has an equals to. So we did a closed circle here. Closed circle means it's included. Open circle means it's not included. Excellent question. One last piece of this. We're going to look at domain and range. One thing that's super duper awesome about piecewise functions is there is a shortcut to find our domain. Because literally the definition of a piecewise function says it's different equations over segments of the domain. Oop, that's not the eraser. These guys are the pieces of the domain. So the domain, we give you. It's part of the process of a piecewise function. And I'm okay if we just copy it down. X is less than or equal to 1. X is greater than 1. Those are 2 pieces of the domain. If we notice and look really, really close, we can see that is in fact everything, negative infinity to positive infinity, or all real numbers. But I'm also okay with us just listing out the pieces. For our range, we're gonna look at the individual chunks. It's just the easiest way to do it. So looking at my purple piece here, what is gonna be my rule for my y's on the purple piece? Are my y's going up or down? Down. So my y's have to be less than or equal to what? -2. So, how about for my green piece? What's my rule for my y's? Greater than what? 2. I've color coded them here so we can see them. If it's not an equal to in the domain, it's not an equal to in the y. If it is an equal to in the domain, it is an equal to in the y. So easy shortcut there too. Here, let me make that higher so you can actually see it. There, just so I saw a lot of people trying to look between people. I can always raise it up higher, y'all. Make sure you can see all the pieces there. Okay. So that's all the pieces. You can see why we're only doing 3 pictures today. It's a lot of pieces and a lot of things there. Okay? These are weird. Wait till when we can do curvy things with them. Questions on this first one? Yes, dear. We're going to go through it again. I promise. Because it's weird. It is weird. I'm with you on that. Yes, sir. Yeah. Okay, these are weird. I'm with you. We're going to do another one. This one has 3 pieces. We can walk through it. I promise we're going to walk through it. It happens. Oh no, shooketh. Totally never happens that the math teacher becomes irritating. All right, so we've got 3 rules here on this one and 3 pieces of our domain. And you can approach this any number of ways. If you like the making the table thing that we did, that's totally fine. So what we're going to do is we're going to take each little chunk and do it one at a time. So I'm going to take my 2/3 x when x is less than 0. So for my purple guy, my x can't be bigger than 0. My x can never be 1. My x can never be 2. My x can never be 6. My x's have to be left of this line. So what we can do is we can pick x values that meet that domain rule. What's up? Yes. Give me a second to write them.
Why does that piece do it?
Because my x's have to be less than or equal to 0. So smaller than 0. Okay. Cool, cool. I'll give you a second. It's totally fine. Once you've got it written down, see if you can pick out some x values we're going to use for the purple one, for the first one. What x values are we going to use? -1 is definitely less than or equal to 0. What's another one I can use? -2. We should also use 0, the one right at our barrier. What we're going to do is we're going to substitute these x values in. 0 times 2/3 is 0. Substitute the 0 in for x. -1 times 2/3. Yep. -2 times 2/3. -4/3 or -1 1/3. We could also do, like, if we don't like fractions, go all the way up to -3, because 2/3 times -3 is -2. So that gives us some points we can plot here. Better? Did it click?
Wait,
I think I just heard that one click.
wait, so you're doing like. So 2/3 is your x. No, 2/3 is your y. You have to multiply everything times 2/3.
It's actually our m. Y equals mx plus b. Anything that's times by an x, that's our x.
Okay.
Okay?
But the x has to be less than 0, so you're just multiplying every x possibility.
We're substituting this in for the x.
Yeah.
Yes.
Multiplying every x possibility.
Yes.
Is this supposed to be x by that 3?
There is not.
Okay.
I will show you. I promise. -2 is -1 1/3. And -3 is -2. So we get this piece here. And we're going to connect it up. And get the whole segment like this. Okay. Our next piece. My x has to be between 1 and 3. So what I'm going to do is I'm going to say my green piece, my x has to be between 1 and 3. If the walls don't help, you don't draw them. My x is bigger than 1, so I put a wall at 1. My x is smaller than 3, so I put a wall at 3. This piece is just between these two green walls. And I feel like the tables are helping, so we're going to do a table here. So what values of x are between 1 and 3? Well, yep. And then we should also use the either endpoints. So we should use the 1, 2 is in between, and we should use 3, right? The equation for this piece is y equals 3. Remember, f of x is y in fancy code. Y equals 3. So when x is 1, what does y equal? 3. When x is 2, what does y equal? 3. When x is 3, what does y equal? 3. Y in a fancy coat equals 3. We're just taking this chunk, I just wrote it out over here.
Y equals 3.
Mm-hmm. So no matter what x is, y equals 3.
Because it's telling you that y.
It's telling you that y equals 3. When there's no x, it just is. And what it looks like is darker green. 1, 3, 2, 3, 3, 3. That's when we get a horizontal segment, a horizontal line. We have one more piece to do on this one. Our last equation here, minus 2x plus 5 when x is greater than or equal to 4. So I have yet another wall here. I have a jump. My x's have to be greater than or equal to 4. And again, if the walls are not helping you, the walls are not a math thing. They're just I think visually they help, but if they're not helping you, they're not helping you, and that's fine.
What else? Oh, the x.
The x's have to be greater than 4. So we're going to make a table. We're going to pick some x's to find the y's.
4.
You said 5? I think, okay, I heard y, and I was just seeing my list. No, 5 is totally fine. 4 is awesome too. And my graph ends at 6. So those are the pieces we're going to try. And we're going to substitute them into our equation. -2 times 4. So -2 times 4 gives us -8. -8 plus 5. -3. -2 times 5. -10 plus 5. -2 times 6 plus 5. Okay. Plot our points. 4, -3. 5, -5. Bless you. 6, -7 is off the graph. But it gives us enough information to get our little piece here. If we were to look this up in like an answer key, it's not going to have your walls. It'll just look like that. This is what it looks like without the walls. Here's the walls. Here's without the walls. I do not care how we have it. Either of these is fine. This is sometimes easier to read. This is easier to make. That's my thoughts on it. But I do not care. It is your graph, it is your paper. If the walls don't help, the walls don't help. I've also been known to have people use Post-it notes and physically make barriers with them. Okay. I'm gonna put the walls back. So, for domain, we've got the cheater version where we straight up just take the list from our function rule. My x is less than or equal to 0. 1 is less than or equal to x, which is less than or equal to 3. X is greater than, that's an x, or equal to 4. When you're looking at your range, use the exact same pieces. So for the purple piece, I'm just going to look at it. What is the range? What is the rule for my y's for the purple piece? Are my y's bigger than or smaller than? Smaller than. So y is less than or equal to, what's the highest? 0. On my purple one. For the green piece, what's going on there? What is my range? It's just 3, right? They're stuck at 3. So we have to kind of smush it together. We're going to use a wiggly bracket, and we're just going to put 3. It's just 3. And then for the pink piece, what's our rule for our y's? Less than or equal to -3. Because my y's are starting here and then going down. On my domain and range. There we go. So those are for all those pieces, okay? We have one more graph to do. I promise it's not as complicated. It's very much set in why we need functions like this. Okay, are you ready for the last one today? Yeah. Yay! Okay, all we have to do is draw the picture. We do not have to figure anything else out. This is legitimately the pricing structure from the U.S. Postal Service. How much it costs to send a letter. If it's between 0 and 1 ounces, it's 47 cents. If it's between 1 and 2 ounces, it's 68 cents. If it's between 2 and 3 ounces, it's 89 cents. Between 3 and 3.54 ounces, it's $1.10. I believe above that, it technically counts as a package. All we're going to do is we're going to take this table and we're going to graph it. There's no equations here because it's a flat rate. The stamp is a flat rate. From 0 to 1, it's 47 cents. So it starts at 0 and goes to 1 at about 47 cents. It doesn't matter if it's a ½ ounce, 3/4 of an ounce, 0.9999999999999 ounces. It costs 47 cents. It is a flat rate. Between 1 and 2 ounces, it's 68 cents. So whether it's 1.000000001 ounces or it's straight up 2.0, it is 68 cents. If it's between 2 and 3 ounces, it's 89 cents, so just under a buck. And then our last one is between 3 and 3.54. It's a $1.10. And it should look kind of like that. What kind of function is this? It's the lines, it's steps, the stairs. Yeah, it's a stepwise function. These kinds of pricing structures are things like parking garages, ticket sales. I can't buy 1.5 tickets to a movie. If I park at a parking garage down at the mall, Circle Center downtown, if I park there for 5 minutes or for 2 hours, it costs the same amount. Because they use a stepwise function for their pricing. Whether I'm in there for 5 minutes or 3 hours, then it'll jump again at 4 hours. And then it's the same there for like 6 hours. Like, it jumps. And if you're there for 2 hours and 59 minutes, same price. It's not scaled. So these are actually used in the real world. Stepwise functions. We don't graph them tons, but these are how they're used in the real world. Okay. So, I'm going to pass out homework 6. It has pretty much, it has 3 piecewise functions for you to look at. It also has stuff we're going to talk about tomorrow. So there's like absolute values that we haven't talked about how to graph yet. We will look at those tomorrow. Okay. Huh? That's okay. You got 5. I understand that. That's why I'm not super keen about it.
I know, you're so happy. I can't.
Sounds about right. About a month in. When this starts to happen. All right, y'all have 5 minutes left in the period. You can start on stuff, or you can just, get yourself where you need to be. Emotionally, physically, whatever.